To the Tournesol talk of today. So we will listen to Sadegh Farhadkhani. Sadegh is a PhD student at École Polytechnique Fédérale de Lausanne, working in the distributed computing laboratory. So happy to hear your story about Byzantine machine learning. Sadegh, it's your turn.
Okay, thank you, Julian, for the introduction. And yeah, I'm going. Sorry.
Oh, sorry, it's my bad. Go ahead.
Okay. Yeah, I'm going to talk about Byzantine robust machine learning and the work that we've been doing in the last couple of years with some people from the lab, and you can see their names here. I'll just try to give an overview over the recent advancements in the field, and I'll try to avoid going too much into the details, and feel free to interrupt me at any point when there's something not clear, and I'll try to explain it. So yeah, we'll start by a bit of motivation. Let's start by a bit of motivation for distributed learning, which is the setting that we usually consider in our work. So there are several reasons for us to consider the learning problem as a distributed problem in different levels. The first reason is that for most of today's machine learning models that we use in practice, the data is usually coming from different sources and different users. And for instance, in the case of GPT, the data is like the text that is generated by millions of people that are not in the same place. So it's natural to assume is a distributed problem as we are using the data from different sources and from different locations. Also, in another level, for computing the model and for the training itself, we may want to use a distributed system because of many reasons like scalability, security, and privacy. And this is what is usually done in the federated learning community. And in this case, we have two different types of federated learning, which is cross-silo federated learning, when we have a few like data centers or some organizations that want to train a machine learning model together using their data without sharing with each other. And also in another type of federated learning, we have like a more fine-grained version, which is cross-device federated learning, in which the computation is directly done on users' devices and like smartphones or smartwatches. And yeah, in this case, might have actually more diversity in data as we have more users in the system. And yeah, these two cases are the case of federated learning, and actually the learning problem is becoming more and more distributed these days. Sorry, like, am I still connected? Because I don't have any feedback.
So we can hear you, but I can hear you like
okay.
Just okay, but
yeah, the sound is not very good, but okay. For me it's understandable also.
Okay. Okay, good, because maybe I can change my input voice.
It's more related to the connection, I think, rather than the...
There now? No different? I changed the microphone.
Yeah, but it's definitely a connection problem.
Okay. Okay, so backward. Okay. Okay, I'll just continue. So let's make the problem statement a bit more formal. So yeah, in the distributed setting, we consider the setting with a trusted server, which is responsible for the training, then orchestrates the training process, which is shown by a like blue shape in this figure here. And we also have
I don't know if
several
it's on Sadegh, excuse me.
nodes. Sorry.
I don't know if it's only me, but
Yeah.
I cannot see the screen anymore. I cannot see your screen.
I can.
Okay.
So now?
For me, it's still not here. Now, if I'm the only one,
You
it's
cannot
okay.
see it?
I don't, but
I
it's okay.
see.
It's okay now.
Oh, okay, good. So yeah, we have n nodes, and each node has a data distribution, and the data distributions are not necessarily the same, which is a valid assumption, because in practice, for instance, for the text data, different users might have different ways of writing, so it's not good to assume that all of them have the same distribution. And because they have different distributions, we can actually define different local loss functions for each user. So here, I call a qi of theta the local loss function of node I. And the goal of the learning problem then would be to minimize the average loss function, which is the average of all the local loss functions in the system. And we also, in general, do not assume the loss functions to be able to include a larger function of the larger class of functions like deep learning and convolutional neural networks. And as we do not consider convex loss functions, we cannot actually hope for finding a local minima in theory. So what people usually do instead is to try to find a point for which the gradient is small, which is called epsilon critical point or epsilon stationary point, which is a point for which the gradient is smaller than epsilon for any given epsilon. So yeah, this is the problem that we want to solve, and the most well-known algorithm for solving this problem is called distributed stochastic gradient descent, or DSGD, which operates in several iterations or steps. And each step of this algorithm, first each node computes a stochastic gradient on its data set, which is GT of I for node I here. And then all nodes send their computed gradient to the server. And then in the next step, the server aggregates all of these gradients by computing their average, and then takes one step in the opposite direction using a learning rate gamma. So yeah, this is the DSGD algorithm, and standard way of analyzing this algorithm is under these two technical assumptions. The first assumption is the Lipschitzness of the gradients of the local loss functions, and the second assumption is that the variance of the stochastic noise is bounded by a given parameter sigma. And yeah, under these two assumptions, there is this standard result. We can show that we have this nice convergence guarantee of sigma over the square root of nt, which is very desirable because it means that if we increase the number of iterations, we can make the error as small as we want. And yeah, so far, everything that I've said is for the good case when there is no failure and all the nodes do exactly what they're supposed to do. But in our work, we consider the Byzantine threat model, which is assuming that some of the nodes are actually malicious and might send any arbitrary vector to the server instead of their true gradients. And yeah, we assume up to like half of the nodes might be Byzantine, and there is actually an upper bound on the number of Byzantines, which is this parameter f here. And we don't make any assumption on what these Byzantine nodes send to the server, and they actually have like full information over the state of the system, and they might like maliciously craft their vector in a way to sabotage our learning system. And now in the the presence of the Byzantine nodes, the objective remains the same as before. We want to find a epsilon critical point, but assuming that up to F nodes in the system are Byzantine and are sending like malicious treatment. And something important to note here is that the server and the algorithm doesn't know which nodes are Byzantine and which nodes are good, so we cannot just ignore the Byzantine because we don't know which of them are good and which of them are bad. Yeah, is it clear so far?
Yes.
It's clear for me, but I guess I'm not the.
Okay. So, asking a pretty question. So, this Byzantine threat model originally comes from distributed computing community, which is meant to capture both things could happen to some nodes in a distributed system. Because we don't have any assumption on the behavior of the Byzantine nodes, it actually captures whatever that could go wrong to some of the nodes in the system. For instance, it could be some hardware crash, or it could be some bugs in the software or network failure, or even worse, it could be some attacker that is trying to like control some nodes in the system. But the most important reason of myself to study this problem is actually poisonous data, because in today's machine learning model, we have like billions of users that are providing data for the model. It is fair to assume that some of these users are not providing like genuine data and like good quality data for the system. For instance, in the case of like GPT, definitely we have some users that are like anti-vax people, and they might want to promote their viewpoint, and they might generate data in order to promote their view. And if our model is not robust to this kind of data, it might actually learn this bad data. And this data poisoning is actually a very active field of research itself. But in order to understand the connection of data poisoning and Byzantine gradient better, we have this work with Lea and Oscar, in which we actually showed that in some learning scenarios, these two attacks are actually equivalent to each other, meaning that any model that can be obtained under one of these two attacks can also be obtained on the other one. And this is a very important result, because it shows that this Byzantine threat model is a very nice theoretical framework and can be used to understand how what is the effect of data poisoning on the models that are trained on user-generated data. And for myself, actually, this is a very interesting research direction, and currently I'm working on is to extend the results to like more general learning models. And okay, so we saw the DSTD algorithm in the previous slides. Now, a natural question to ask is whether this algorithm is Byzantine robust or not. And the answer is no, and the reason is that for the DSTD algorithm, we aggregate the input vectors by computing the average of the input vectors. And averaging is actually very fragile, and it can be manipulated by a single Byzantine node. And you can see this in this figure on the left, in which we have two honest nodes, and they are sending vectors that are pointing to the right. But there is also one Byzantine node that is sending a vector to the left, but with like much larger magnitude. And now if we compute the average of these nodes, the final output is going to also point to the left, which is exactly the opposite of what the honest nodes want. And this shows that this single Byzantine guy can actually manipulate the output of the aggregation function arbitrarily. And this is why averaging is not Byzantine robust. So in order to make the algorithm Byzantine robust, what people usually do is to replace averaging with a robust aggregation function or robust aggregation rule, which I'm denoting by F here. So yeah, instead of computing the average, we compute like a non-linear function of the input vectors and then take one step in the opposite direction. And now the question is how we should choose this F, because choosing this function is actually challenging because there is like disagreement between what different honest nodes are proposing and the vectors that each honest node is proposing. And the reason that they are proposing different vectors there are two reasons. The first reason is that each honest node is computing a stochastic gradient, so there is actually a noise in the gradient computation. And the second reason is that there is also heterogeneity in the local loss function. So even if each honest guy computes its full gradient, they're not going to send exactly the same vector because their data distributions are different and they are computing the gradient of different functions. And in order to be able to obtain some positive results, what people usually do is assume that the heterogeneity is actually bounded by a parameter, which I'm calling zeta here. So yeah, this parameter captures how different the local loss functions are. And if it's equal to 0, it means there is no heterogeneity in the system, but usually it's not 0. And yeah, the larger it is, it means that the data distributions of the nodes are more different parameters. So yeah, as I said, if there was no heterogeneity and there was no stochastic noise, then all the honest nodes would send exactly the same vector, and we could actually use a majority voting to find this honest vector, because we assume that the honest guys are the majority. But in the learning problem, we do have a stochastic noise and we do have heterogeneity, which means that we cannot just simply do majority voting. And that's why there are like many different papers proposing different aggregation rules and trying to robustify the SGD algorithm by these aggregation rules. Here we can see some of these rules. The first one, like the first family of these aggregation functions are the coordinate-wise aggregation functions, which treat each coordinate of the input vector separately. So for instance, we have coordinate-wise median that computes the median of the numbers sent by the honest users in each coordinate. So in this example here, we have 5 users, and each user is sending a two-dimensional vector. So the first user is sending 3, 6, the second user is sending vector 1, 2, and so on. And what coordinate-wise median does is to compute the median is in the first dimension, which is the median of 3, 1, 3, 6, 8, which is 3, and not computing the median in the second dimension. And this aggregation function is actually robust because if the Byzantine nodes send like very extreme values, it's going to be ignored in the computation of the median. And yeah, this is coordinate-wise median, and we also have coordinate-wise trend mean, which is similar. And in this one, we actually remove the f smallest and f biggest numbers in each dimension. Here, f is equal to 1, so we remove the smallest value in the first dimension, which is 1, and the biggest value, which is 8, and then we compute the average of the rest of the numbers, which is going to be 4. And yeah, this aggregation function is also robust to F Byzantine nodes, and it kind of intuitively is better at estimating the average of the honest guys, because here we are actually computing the average of several numbers. And yeah, both of these aggregation functions are analyzed in some works before. And we have also some like more sophisticated aggregation functions like the geometric median or minimum diameter averaging, but I'm not going to discuss these ones in detail. Just wanted to mention it here. There are like many more aggregation functions like Niamed, Krugman multichrome, which was kind of the first aggregation function that was proposed and like kind of started this field, and like many more. So what we observed about these aggregation functions was that often they are actually analyzed by different forks, and they are actually analyzed under different sets of assumptions. So it was not actually possible to see which aggregation is better than the other one and which one should be used in any specific machine learning problem. So what we did to remedy this problem was to propose a unifying framework that allows us to analyze all of these aggregation functions under the same set of assumptions, and being able to compare them using like the parameter that says how good each aggregation function is, which is this paper that was published in ICML on the left here. And then next paper follow-up, we kind of improved result, like this improved our analysis, and also we proposed way to make aggregation functions like better and more robust. So like I'm not going to go to the details for these papers, but like one important result that we have is that the coordinate by streaming algorithm that I presented in the previous slide is actually optimum in a precise sense that we are going to see, and we can also make other aggregation functions optimum as well by using like some application steps. But coordinate streaming is optimum itself; it doesn't need any extra step or anything. Okay, so as I said, there are two different reasons that the honest was in different vectors of the server. And the first reason is the stochastic noise, and we had this assumption that the variance of the stochastic noise for each honest user is bounded by sigma. And now to reduce the effect of the stochastic noise on the learning and to reduce the error that is caused by the stochastic noise, what we need to do is to reduce the variance of the updates that are sent by the honest nodes. And there are several ways of reducing the variance. The first one is just to use a large batch size. So instead of computing the gradient on a single data point, each node can compute the gradient on a batch of data points, and it will actually reduce the variance. And this is a perfectly fine solution. It might work in some scenarios, but the problem with this is that it will increase the gradient overhead. So each node will need to have more data, and it also increases the computation complexity for each node, which is not desirable. So what we can do, which is more smart, is to use like variance reduce optimization techniques like polynomial momentum. And this is what we do in our work. So in this work, it is exactly the same algorithm as the one that we had before. Then the difference is that instead of sending the stochastic gradient vectors GTI, first each honest guy computes the momentum vector with this equation here, which is like p times mt minus 1 times 1 minus beta plus 1 minus beta gt. First each honest guy computes the momentum vector, and then they send the momentum vector to the server. And the server does exactly as before, which is computing the aggregation of the momentum vectors and taking one step in the opposite direction. And the nice thing about momentum is that it will actually reduce the variance of the updates by a factor equal to 1 minus beta. So if we choose this parameter beta like close to 1, we can actually mitigate the effect of the stochastic noise. And for the learning problem, it means that if we combine momentum with like an optimal aggregation functions like coordinate by stream mean, it will lead to this nice convergence guarantee of like sigma squared divided by t plus 1 times 1 plus f divided by n. So if you remember from the first slides that we had, in the non-Byzantine case, the convergence guarantee was sigma squared divided by nt. So the difference here, this is this parameter f, which is added here. So it means that we have actually like a linear overhead in terms of the number of Byzantine nodes in the system, which is kind of the cost that we need to pay due to the presence of the Byzantine nodes. So it was the stochasticity, and the second source of disagreement among the nodes is heterogeneity, and this one is actually more fundamentalist and it's more challenging to deal with because there is actually a very strong lower bound which says that no algorithm can actually obtain an error less than the fraction of Byzantine nodes, the fraction of Byzantine nodes times the heterogeneity parameter. So it means that no matter what we do, no matter what algorithm we use, it's not possible to do better than this. I mean, we can actually match this lower bound by using coordinate string mean, and that's why I said it's optimum. But the problem is this lower bound actually could be very, very large, especially when the dimension of the model is large. For instance, for GPT-3, the dimension is like 10 to the power of 11. So, and also the data is coming from like a large number of users. So this parameter's data is arguably very, very large, which means that even if there is like a small fraction of Byzantine nodes in the system, we have a very, very large lower bound that might any kind of convergence guarantee like vacuous. So this is actually a very important security issue in the cases that we train a machine learning model, like a high dimensional machine learning model on user-generated data. And now currently we are trying to better understand the this lower bound and the effect of heterogeneity on the learning problems. So yeah, combining the two sources of error that I mentioned, we get this convergence rate. So the main point to the main thing to point here is that the error that is from the stochastic noise sigma squared is actually vanishing with t. So if we increase t, it will completely vanish. But the error that is coming from heterogeneity is there, and there is no way to reduce it. Okay, so far everything that I said was assuming that there is a trusted server and like it doesn't fail, it's not malicious or anything. And yeah, all the results that we had was based on this assumption, but this is a strong assumption and not very desirable in practice because, for instance, there are some works showing that when there is a server that is responsible for the training, the server actually is able to put some like backdoors in the model that can be used in the future. So if the server is malicious, it can be like a very, very important security issue. So it's not desirable. And because of this, we have also decentralized learning in which there is no central server and the nodes directly communicate with each other instead of sending their messages to the server. And yeah, we also consider this setting in our works, which is like Byzantine learning in the decentralized case. And considering this, actually, considering the decentralized case, we will have one additional challenge due to the presence of Byzantine node, which is in the decentralized case, we have model drift, which means that at each point in time, there is no reason for the local models of different nodes to be the same. So if we are not careful in designing our algorithm, and if you're not careful in designing the algorithm, these models can actually diverge from each other to different points. And in this case, the gradient computed by one honest node is going to be useless for the other ones. And this is the extra challenge that we needed to tackle. But we have a very, very recent result, which is going to be presented next month in ICML. In which we could actually obtain exactly the same convergence guarantee as the parameter server setting, but without relying on a trusted server. So and this algorithm again uses momentum plus nearest neighbor averaging algorithm, which filters out the vectors that are very far from the node, the vector of the node itself, and averages the rest. And it's a fairly simple algorithm, and we could show that it achieves exactly the same convergence guarantee as the best result in the parameter server setting. And these are the works that we did for the decentralized case. I think this concludes my talk. Thank you for your attention.
Thank you. Thank you for the talk. If there are questions?
I do have one.
Okay.
Did you think about the case when the exchange of gradients is asynchronous compared to lockstep situation like that?
What is asynchronous? Sorry, I didn't hear.
So in your setup, let's say gathering of gradients from the worker and computation of the next step for the model is completely synchronous.
Okay.
And did you think about some variation that introduced some asynchrony between the worker speeds?
Okay. This is a very good question. In the parameter server setting, we also always consider the synchronous case, but in the decentralized case, we have the assumption that the communication links are asynchronous, but I think it's a bit different from the notion of asynchrony that you mentioned. Here, we assume that the links are asynchronous, which means when a node sends a message, there is no bound on the communication delay. Like, this is the definition of asynchrony mostly in distributed computing, which we consider here. But the one that you said, no, we don't consider that one, I think.
So, but they can, in the decentralized setting, they can have let's say, different version number, let's say, for the model when they are exchanging their.
So in this case, what we do is to have iterations. So at each iteration, each node sends its model to other nodes, and then waits until it receives a fixed number of models, and then goes to the next iteration. So there is not asynchrony in the gradients that are aggregated.
Okay. So I have another one if nobody's.
Okay.
So the original paper, what was the aggregation function that we used? It was the one that you called minimal diameter, that's it, in machine learning with adversaries.
It was Chrome. In the first paper, it was Chrome, like Chrome and multiple.
Yeah, that's it.
Yeah.
to the aggregation function because minimal diameter, that's it? Or I'm not sure.
No, minimum diameter is a different one. Like it's one that we used in one of our decentralized papers. But Chrome and multi-Chrome, I don't have them in that slides.
Okay, so geometric gradient. Okay. I should know, but
No, like I don't have it. I don't have the Chrome in this slide. It's just mentioned here.
By the way, Sadegh, Julien is one of the co-authors of the Chrome paper.
Okay. I mean, I didn't know. Okay, sorry for not having it here.
no, don't worry.
So if nobody has a question, I have a question. Like, so you said that the coordinate-wise twin mean is optimal?
Yeah, Clay, expected to ask this question. Yeah, it's actually optimum. Like in the new definition that we have, in the new definition of robustness that we have in the AI stuff paper. Yeah, in this one, fixing by fixing, we could actually prove that coordinate-wise training alone can match the program due to heterogeneity. So in this case, it's optimal.
Okay, is it like the C averaging notion? I guess it's not. It's
no, it's a bit different. Like instead of having the maximum on the right hand side, have the average. Like it is one difference. And also the thing about like a square Euclidean norm is that if you have the inequality in one dimension, you can't just add all of these inequalities in all dimensions and you get it in the full vector.
okay.
Okay. Yeah, I think it's because we changed the maximum to the average, because with maximum we could not do that.
Okay, interesting.
I have a
Interesting.
non-technical
So, yeah.
question.
So for practical deployments, sorry.
Sorry, you wanted to continue on the...
Go ahead.
Okay. So non-technical
No,
question, it's like you have so these nice theoretical results where you obtain bounds on like how much you can control in these different environments that are more or less like problematic. And so these bounds are nice, but like practically, could you say like what it's telling us in a practical situation? Or is it I'm not even sure if it's easy to answer, but like in a practical situation, based on these bounds for which you have algorithms that are able to do the job, in some sense, how difficult would it be to, I mean, how good are these bounds in the sense like it will be extremely or more or less difficult to really have a system which is robust in practice? Like, is it telling us something like in some sense, like can we reach it in practice in large scale developments?
It's a very, very good question. I mean, we also do have some experiments in this paper. I mean, I don't have here because I'm like mostly theoretical, but yeah, we do have some experiments in the scale of the experiments are not like large scale. It's like maximum we consider CIFAR 10. So in the largest scale, if you mean like training GPT, I would guess it would be very, very difficult with Byzantine nodes. But like in the experiments that we consider, the last, like this fixing by mixing paper, the effect of Byzantine is really small, like in the experiments that we have. Like it's fairly close to what you get even without Byzantine.
Okay. So
You can actually see that like the aggregation function, which is good in theory, also yields like a better convergence behavior in practice.
I see. Thank you.
But actually, we never tried to test it on like more larger scale models. I mean, I'm not sure what happened.
So I have a related question. Is like many of the results is like in the parameter space, like or like the gradient of the loss. I guess like from a practical point of view, what would matter more is like if you can show things about like the actual algorithm, like the output of the algorithms on given inputs or something like this. Like, do you think this can be a theory that, like, how vulnerable? I'm not even sure how to phrase it yet, but like even writing a conjecture is hard. But yeah, like, can you have a theory of how poisoning can impact like the output of the algorithm in the end?
I mean, the thing is, if you consider non-convex functions, it's already very difficult to have the convergence guarantee on the norm of the gradient. Yeah, the thing is, having the convergence guarantee on the norm of the gradient itself is a very, I would say, weak guarantee, but this is the best that we could do, because we might have some saddle points that have like a huge loss, and the norm of the gradients is very small. So even without Byzantines, it's hard to say stuff like this in the non-convex world. But if we have some like convexity assumption or even strong convexity assumptions, I think we may be able to. We probably will be able to like what would output will be in the presence of the continuum, because I think in that case, a bound on the norm of the gradient would translate to a bound on the function value itself. So,
what about the set of Byzantine adversaries that are trying to get you stuck in the local minimum? So exactly the contrary. They try to make you stop.
so you said the Byzantines that try to converge
To make-
the model.
Yeah, to help you, between quotes, to force you to stop because they put you in the local minimum.
Yeah, I mean, this is also a possibility that is not captured in the theoretical work. But it would be very interesting to study this as well. Actually, this is a very, very important, very interesting point, because we might have like some saddle points and it perfectly matches the theory that we have, and they are very bad. So if the Byzantine nodes can bias the model to those points, the theory is good, but the model output is not very good. So
Yeah, and all the differences are fighting you against the other direction.
yeah.
Yeah, I guess this is well. I guess my question was also related to what we're doing on Tournesol, where like the output is like the scores, so it's like kind of the parameters, so we can have a better control over it. But yeah, I think it would be nice to. I mean, yeah, I haven't analyzed, like, for instance, Tournesol's algorithms in a distributed setting. I guess it's too early, but it would be interesting to know, like, for a convex problem, like what kind of guarantees you can have.
Yeah, you probably know that, but this is the only paper in which we discuss the parameter space instead of providing the bound on the gradient.
Yeah. Yeah, we even have the output space because we do reprogramming of a labeling function here. So what are the future works?
Future works, okay, we have several future works. I don't have any slide, but one thing that I'm currently interested in is to reduce the communication cost in the decentralized case, because currently in our algorithms, all the nodes need to send their models to all other nodes, and this actually induces a very large communication overhead. So what I'm trying to do now is to reduce this communication overhead by using like subsampling and only communicating with a subset of the nodes. And another one is to better understand the connection between data poisoning and and Byzantine gradient attacks in like more general cases and more general learning problems. I think like the most general case would be the non-convex setting, which now I'm currently working on that.
For the distributed setting, you assume public key cryptography and key distribution before, or you're unable to lying during repetition by node, thing like that.
Okay, I didn't hear very well what you said. Sorry.
I'm sorry. Do you assume that you have a signature, unforgettable signature in the distributed setting, or not?
Do I assume we have signature? This is what you said.
Yes.
Okay. Yeah. I mean, for the communication, you usually assume that the nodes know each other and the messages are signed. So one guy cannot forge a message saying that it's coming from another guy.
Yeah, but when they are relaying messages saying this node told me that, can they lie?
When they're relaying, I mean, if the message is signed and it can be verified by the receiver, so it cannot be.
Yes. Well, if you just assume that the channels are authenticated, then they can lie.
Yeah, but I mean, what I said is that even if we assume that they are relaying the messages, it will still induce a very large communication overhead.
Okay.
Yeah. Okay, is there any other question?
Do you look at what's happening on the Flower network or practical network for distributed learning?
Like in different architectures, you mean?
No, there is one by the people that made Bloom, which is called Flower, I think, or Flip, I don't know. That is like federating individual hardware in order to do some distributed learning. I don't know if they have different things against malicious nodes.
Okay, I really don't hear you very well. I don't know why. The voice is not very clear.
I'm sorry, I'm gonna go out of the metro now. You better now?
I think yes.
Yeah, I was wondering if you looked at the Tulip network, I think, from the people that made Bloom, which is a distributed learning network where people are putting their own hardware in the federation to do some distributed learning. And I'm not sure they have any defenses against malicious nodes, but I wonder if you look at.
Okay, no. Okay, no, I see what you mean. Not really. So in our work, we usually just assume there are like a specific number of nodes and they're independent. So not really, but it would be very interesting to look at, I think, in the future work.
Okay, if there's no more question, I think we can end here.
Okay, good.